Thank you. Thanks, everyone. So let's actually start with a little bit of history. So this is Lyft from about 4 years ago. And as you can see, this is our, quote, simple service-oriented architecture. And we've got, I guess this is going to work, probably not. So we've got some clients, we've got the magical internet, we've got an Amazon Elastic Load Balancer, we've got a PHP Apache monolith, and we're talking to MongoDB. This is about as simple as it gets. And even at this very early stage, we're already seeing a bunch of problems here, right? So we've got load balancer, which we can't actually look into. We can't actually get accurate stats from P99 to P99.9. We can't actually get to the logs. We've got MongoDB that we don't actually run, so we're paying someone to run MongoDB, and actually understanding failures in terms of CPU kind of usage and all the things that are going on behind the scenes is actually quite difficult. So even at this very early stage, we're already seeing problems. So let's fast forward to about 2 years ago, and this is what Lyft's architecture looks like. Again, we've got clients, we've got the magical internet, we've got the load balancer, we've still got our monolith. We're starting to decompose this monolith, and now we've got a whole bunch of internal load balancers, we've got a whole bunch of Python services, we've got 2 data stores now in terms of Dynamo as well as Mongo. And this is actually starting to be a tremendous mess. We have whole bunch of different libraries that people are actually using. So we've got our PHP service-to-service libraries. We've got our Python libraries. We've got different libraries talking into our data stores. So whether that be Dynamo or Mongo. And because we now have not only one load balancer, but we have many internal load balancers, we actually start having kind of a multiplicative effect of stat problems, where trying to understand failures, it's almost impossible to understand, are those failures happening in the individual application? Are they happening within the load balancer? Are they happening within Amazon's infrastructure? So we start getting massive developer confusion in terms of what's actually going on. So let's step back and kind of based on that architecture of Lyft from both 4 years ago as well as 2 years ago, let's look at kind of the current state of the art in service-oriented architecture networking. So we've got a whole lot of different languages and frameworks. So we've already seen that, we basically have PHP and Go and Python and Scala. So we've got tons of different applications out there. We have a whole lot of different protocols. So we have H1, H2, we have gRPC, we have different databases, we have different caching. We have a whole bunch of different infrastructures. So that's infrastructure as a service, containers as a service. We have people that are running on-premise. And then we have all kinds of different load balancers. So those are virtual load balancers. Those are hardware load balancers. And then most importantly, you've got this entire mess of things, right? You have different languages, you have different protocols, you have different infrastructures, you have different load balancers, and you're trying to figure out what's actually going on. And that typically boils down to stats, tracing, and logging. And the problem that most people have in this situation is that all of these different components are spitting out different stats, no tracing typically, and different logging. So from an operations standpoint, you're trying to understand what's actually going on in your system, and it's almost impossible because you're trying to look at these different things and they don't quite line up, and the cognitive burden of actually understanding what's going on is almost impossible. And then next, because of all of these different stacks and all of these different libraries and frameworks and kind of different programming languages, we've got a whole bunch of different implementations of important things such as retry, circuit breaking, rate limiting, and timeouts. So these are things that we're all told that we should do, right? These are really important when we're building these large systems, but people typically don't have them. And when they do have them, they might have bugs or they might be implemented 6 different times, and it becomes quite complicated to kind of understand when we actually get into a particularly bad situation, are all of these things going to kick in correctly? And then most small companies, they might be thinking about kind of authentication from an external source, but from a service-to-service perspective, kind of notion, most companies are not doing any authn or authz. And lastly, I've already touched on this, but we typically have, again, many per language libraries. So the way that most people are building systems today is they'll have a particular library for Java, or a library for PHP, or a library for Python. And these things, they do some stats, they do some logging, maybe if you're lucky, they do some tracing, and they'll do some timeouts and some circuit breaking. But they're often partial, and they might have some bugs. And if you want to do something new, you have two problems. You have to re-implement this functionality in all of these libraries. So since most companies today are not lucky enough to have a single language, they're typically what we call polyglot. You either have to staff up a team to implement these libraries across 5, potentially 6 different languages, or you have to suffer kind of the reality that there's going to be 1 or 2 first-tier best languages that work correctly, and then there's going to be some second-tier languages that maybe work, and then everything else is pretty much not working. And then from a library perspective, the other thing that I'm sure most of you have actually dealt with is that when you want to upgrade those libraries, you have to go and you have to beg and plead potentially hundreds of service owners to actually do those deploys, right? And that is an incredibly painful situation to be in. And it's one thing if you're trying to get people to actually ship new features, that's great, but let's say that there's some type of CVE. And you're going around to people and saying, OpenSSL just has this big vulnerability. I need you all to deploy right now. You still have to go around and beg and plead hundreds of services to go and actually do that deploy, and that's a super painful place to be in. So this is generally what I think most people experience when it comes to networking, right? It's incredibly painful. It's incredibly confusing. And no one really knows what's going on, to the point that I think for many smaller companies, if you're not Google or you're not Facebook or you're not someone that's invested a lot in this space, many developers don't want to do SOA. They just don't want to do it, right? Like everyone says in the industry now that SOA is the future and everyone should do microservices. But when the rubber meets the road and you go talk to developers, there's so much confusion in terms of debugging, in terms of observability. There's so many different things out there in terms of the libraries that they just don't trust the network. They don't understand when things are going to go wrong. They don't understand how to debug. And they would prefer to just stick with their monolith or ship fat libraries and kind of do all of these things. So we're in this interesting situation now where I think everyone recognizes that there's a lot of benefits to the microservice architecture, but we don't have the tools yet that actually enable most people to get out there and build quality architectures. So what is Envoy? So kind of the mission statement, which I'll just read, is that the network should be transparent to applications. When network and application problems do occur, it should be easy to determine the source of the problem. And that's a great mission statement, but it turns out to do that, it's really hard. So what does Envoy actually do? So Envoy is a proxy, so it's not a library. It's an actual server, and there's different kind of things that people are calling it these days, from the quote sidecar model to the service mesh proxy. But really, at the end of the day, it's a server like HA proxy or some other server, and we run it alongside every application server. And the idea behind this is that you implement a lot of these really hard things, which I'll get to in a second, but you do it once, and then you don't ask every application and every library to re-implement it 6 or 7 or 8 different times. It's written in C++ 11. I won't talk any more about this. That was done mostly for performance. At its core, Envoy is a kind of a filtered byte proxy. And by that, I mean bytes come in one side, they might get transformed, and then bytes get spit out the other side. And that's a really useful framework in the sense that it can be used for all kinds of different things, right? We can use it for Mongo, we can use it for Redis, we can use it for something like S-tunnel replacement. We can use it for TCP rate limiting. And of course, we can do all of the H1 and H2 processing that we all know and love. And once we get into kind of the REST layer, there's a second set of filters there. So whereas the byte filters are going to process again on bytes in, bytes out, we've got this second filter layer, and that filter layer is going to process on things like headers and body data, right? And that's going to allow us to actually build really complicated layered functionality. From a proxy perspective, this is an H2 first proxy. Most proxies that are out there today are still H1 proxies, and they have actually very limited H2 support to the extent that most proxies can support H2 connections on the front side, but when it comes to the back side, they can still only support H1. There's actually very few proxies out there that are fully BiDi in the sense that they can do H2 and H1 on both sides. Envoy has built-in service discovery, so that's basically finding what are the upstream hosts to actually talk to, and it handles both active and passive health checking. So active health checking is actively saying, hi host, here's /health check, tell me if you're up. Passive health checking is starting to look into things like, did you return 3 500s in a row? Let me actually boot you. And we do a whole bunch of things in the advanced load balancing realm. So that's retries, timeouts, circuit breaking, rate limiting, request shadowing, outlier detection. And I'm going to talk a ton about this, but really it's all about observability. And that's going to be stats, logging, as well as tracing. And finally, Envoy is also usable as an edge proxy. So that means that it has full TLS support, and you can use it for basically routing and terminating client traffic. And you might ask, why would I do that when I can use something like Nginx? What we find is that using the same set of software, both on the edge as well as within your data center from an operations perspective, it makes things much, much easier. Again, you don't have to have multiple different kinds of stats, multiple different kinds of logs. So this is what kind of, at a super simplified level, this is what an Envoy service-to-service topology looks like. We have multiple service clusters. We've got obviously a bunch of service nodes within those clusters. We have an Envoy running alongside, in parallel, alongside each service. It doesn't matter whether the service is written in Go or PHP or Python or Scala or Java, it doesn't matter. Those envoys talk to each other. They can use different protocols. Typically, they use H2. And then those envoys can also talk to external services, whether that's MongoDB or Dynamo or Stripe or other vendors. And then those envoys are talking to a service discovery service, which allows them to know all of the hosts. So this gets us to Lyft today. So we looked at Lyft from 4 years ago, which is that very simple architecture. Lyft from 2 years ago, which was kind of a mess with a lot of confusion and arrows going each and every different way. And now we get to Lyft today. And what this looks like is, again, we have our clients, we have the internet. The clients ingress through front Envoy proxies. And that's, again, so that we can run the same software on our edge. Because when you actually think about it, 90% of what an edge proxy does in terms of routing and load balancing and circuit breaking and forwarding is exactly the same as what service proxies do. And then each of the front envoys, they're going to route to our still existent legacy monolith, which is running Envoy alongside of it. And now we have a whole bunch of Go services, a whole bunch of Python services. Every service that we have runs alongside Envoy. So all traffic transits through Envoy. And then on the back end, from a data store perspective, we've got MongoDB, we've got Dynamo, we've got stats and tracing, and those all come direct from Envoy. And we still got our service discovery service. And what we find here is that, which I'll actually get to in a second, is that this base layer running this proxy alongside each application, it gives us not only features, but it gives us amazing visibility. Let's talk briefly about service discovery. Most companies historically, they do service discovery using very popular systems like Zookeeper, etcd, Console. what I've always found pretty interesting about this is that these systems are fully consistent. And what I found from my own experience is that these systems typically are hard to run at scale. So most of the companies that I've worked with, they have a team that works on Zookeeper. They have a team that works on etcd, and these things tend to fail a lot and require a lot of care and feeding. And one of the things that we did when we started working on Envoy is we realized that service discovery is an eventually consistent problem. It's not fully consistent. It's not required that every node has an exactly synchronized view of every other node. It's sufficient that every node eventually converges. And one of my general principles of kind of doing these types of things is that if you can take a fully consistent problem and you can make it eventually consistent, you might as well make it eventually consistent. So what we did is we designed Envoy from the get-go to treat service discovery as lossy. So we assume that hosts come and go. We assume that the service discovery service can basically be killed. And what we end up doing is we use active health checking from each Envoy along with the service discovery service data to produce a routable overlay. And this gives us this 4x4 matrix. And if you look at this matrix, what's really important here is we trust the active health checking data more than the service discovery service data. That ends up being critical because, again, we just assume that that service discovery service, which could be implemented on top of something like Dynamo or even something fully lossy like Redis, we assume that it can go away at any time. And little anecdote is during the recent Amazon outage for S3, you wouldn't think that that would have any implication here. But it turned out that at the beginning of our check-in process, so each one of our hosts at Lyft, every 1 minute, it actually checks into the service discovery service. There was a kill switch at the beginning of that script that was calling out to S3, and that script was actually failing to run. So the hosts were not checking into discovery. And within about 5 minutes, all of the hosts had been swept from discovery, and now we have no hosts in discovery. So Lyft was fine, right? Because again, we assume that service discovery data can be completely blown away at any time, and that when S3 came back up, that bug ended up kind of being fixed on its own, and then we started to check in again, and the data eventually converged. And we obviously could have gone out on the host, and we could have fixed the script, right, so that we don't get hit by this S3 bug. But we actually made the decision that why risk doing that during this outage when the system is working essentially perfectly as designed. So let's briefly go through kind of the load balancing features that Envoy supports. So as I talked about before, it supports a bunch of different service discovery types that ranges from static configuration to different types of DNS to actually talking over a REST API to fetch hosts. We call that our service discovery service API. We do zone-aware least request load balancing. So if you run in a system like AWS where you have different zones for both cost as well as availability reasons, it's better if you can favor your local zone because Amazon actually charges you for cross-zone traffic, and your traffic will transit more routers. So it's more efficient and lower cost to actually do this. We do a whole ton of stats, which I'm going to show you, but we basically build out stats for per zone stats. We have canary stats. We have all kinds of stats. We do a lot of different types of circuit breaking. So that's circuit breaking on max connections, requests, as well as retries. We do rate limiting. We actually integrate with a global rate limiting service, which we recently open sourced. So this allows Envoy, based on different types of configuration, to call a global rate limiting service and do rate limiting in a fairly generic way, whether that be by user or by cluster or by some other metric. We do shadowing, so we can actually fork traffic to a test cluster. This has been a pretty popular feature with our devs. We have built-in retries with different policies. We do a whole bunch of stuff with timeouts. So we have both outer timeouts as well as inner timeouts. Reason that's important is that we actually encourage our devs to use a combination of both timeouts as well as retries and set reasonable kind of inner per try timeouts and then set a global timeout. And then we use exponential backoff for those retries. As I was talking before, we do outlier detection. We have a kind of other stuff that's coming in this area, but right now we do consecutive 500s. With this system, we can do deploy control, whether that's blue-green, stuff like that. And then we have written the code to do fault injection. So that's basically injecting, 500s or injecting latency. We haven't rolled this out yet in production. That's a Q2 thing. So let's talk about observability. So I've already talked about this a few times, but from my perspective, from operating kind of a large architecture like this, the most important thing that something like Envoy provides is enabling developers to quickly understand what is going on in the system, where are things failing, how is it performing. So Envoy, by having all traffic go through Envoy, we can get a few different things that are really useful. One of them is to get the same stats for every hop. So since we run Envoy both for ingress as well as egress, we have very consistent stats for each hop, which I'm going to show you. We can create and propagate a stable request ID as well as tracing context. So this is super important because this actually allows us to do kind of logging as well as tracing and actually do consistent sampling. So if we sample, say, 1% of particular requests, it's not that we sample, randomly 1%, which is pretty useless. We can actually sample 1% of requests that flow throughout the entire mesh, which is actually pretty awesome. And then we can do consistent logging, and we can do tracing, which I'll also show you. So this dashboard here, so what we end up doing at Lyft is we actually generate a whole bunch of dashboards for people. So the idea is that we don't want people to kind of randomly pick and choose all of the graphs that they actually look at. So for the most part, we do we spend a lot of time trying to make sure that whether it be for Envoy or whether it be for Dynamo or for Mongo or for different things, we have templates. When people make a new service, we actually give them most of the rows that show up in their dashboard. And what you're looking at here is the kind of the top row for the auto-generated dashboards that we give service developers. And all of this data comes from Envoy, and it doesn't matter, again, whether the service is written in PHP or Go or Python or Scala or Java. And you have all of the basic stats that you would probably expect, whether it be response time or call volume or error rate. And then on the left side there, we actually have links that take you out to our logging system as well as our tracing system. This is a cool one, and this is a service-to-service template dashboard. And what you'll see here is that on the upper left-hand side of this dashboard, it's actually a template. And there's two drop-downs, and you can pick the origin service and the destination service, and every service at Lyft is actually populated there. And the developer can just choose, I want to look at all of the traffic from this point to this point. And then we auto-populate dashboards using Envoy data. I've only showed you the top half, kind of the outbound portion. And then on the bottom half, there's an inbound portion. And what this allows you to do from a dev perspective is that if you're getting errors between two services or you're trying to understand what your call volume looks like or kind of different things, you can immediately go here and you can get all of the top level stats and you can get details about failures, errors, retries, stuff like that. This is our global health dashboard. So this is actually the aggregation of all traffic from all envoys. And this gives us the ability, kind of like from a NOC or like a network health perspective, to go through and look at kind of the entire system. So this is typically the dashboard that I look at if I want to know kind of overall system health, right? But it's incredibly powerful because we're seeing where you can kind of look at this and say, oh, there's something failing or not. Then I can drill down and figure out, okay, it's between these two services. I can go back to my service dashboard, or I can go to the particular service rows. Here's our tracing system. So this is, again, there's no service code written to actually do this. We rolled out tracing at Lyft without asking service owners to do absolutely anything. And we rolled it out across, again, PHP, Go, and Python. And this is tracing all the way from the app. So this is a request coming from the iOS client. This is coming into our data center. For size, haven't actually dropped down all of this, but you can see that there's a bunch of different service calls there, and then, actually flows back to the client. And then in terms of logging, as I was saying before, we've got this stable ID, and this stable ID allows us to link all of those traces and link it back to our logging system. And then from there, we have devs who can go in and they can basically search on particular request ID, or they can search on all kinds of different things. So let's talk briefly about Perf. I think most companies that are here that aren't Google or aren't Facebook, I think most people would argue that dev time is worth more than probably computer costs. But what I think people don't think about very often is the cost of tail latency. And by tail latency, I mean like looking at things that happen out at like P99. And what I found is that even at small companies, developers who are trying to meet particular SLAs or things like that, they're going to become very focused on, I did 1,000 requests. Why are 10 of them failing? It seems really bad, right? So this whole concept of not caring as much about throughput, but caring very much about that tail latency is actually super important. And we're in the interesting point right now where most of the work that's done at most companies now uses, super convenient things, right? We use languages that have garbage collection, super productive, but they have very odd tail latency properties. We use virtual infrastructure, again, super convenient, but you don't really know what your noisy neighbor is doing or what your cloud provider is actually doing. So all of these things, they're super awesome, but they make debugging really, really difficult. So at the end of the day, you've got this system, and it's really important, though, to be able to understand what the underlying performance is. And if your proxy itself, if you can't rely on the data that your proxy gives you, you've got this physics observer effect, right? Where like if the thing that is doing the observing cannot be trusted, then the entire underpinning of all of your stats kind of becomes very problematic. So this is the main reason that Envoy was written in C++, and it's the reason that we take performance fairly seriously, because we believe that this system enables us to actually go through and focus, devs on where their time is better spent while having very, very accurate data. So let's talk briefly kind of about how we manage the configs, because when you're running these large architectures, it can become fairly complicated. So what we actually do for Envoy is we have kind of a multiple step process of doing config management. So we have a bunch of Jinja JSON templates. Those are spit into our build and our build process, and then we get we get the output of that, and then we end up running salt, for process management, and then. We have all the services, and those services end up, going through their. Sorry, one sec. Sorry, one sec. Sorry, yeah, so we've got the service manifests, and then services specify who they actually talk to. So those services end up actually saying that they talk to particular services, and then we bundle all of that data, and we essentially run it through Jinja, as well as Salt, and then we wind up with these configs. This has actually worked fairly well for us, but what we're actually finding right now is that we end up having to do a whole bunch of deploys to, kind of get these configs out. So what we're working on now is to actually get a central config service running, and this will allow us to actually put a bunch of this manifest data in one place, and then actually spread that out from an automatic perspective. So one of the things that we end up doing with Envoy is trying to figure out how to actually talk to different services. And this whole service mesh system, it's somewhat magic, right? But there's still code that has to run in each service, whether that be Python or whether that be PHP or whether that be Go. So what we've ended up doing is we have these thin clients. So here's an example of a Python thin client. And this is a Python service calling a service called Switchboard. And what you're actually seeing here is that from the user perspective, they basically instantiate this Envoy client, they call the service Switchboard, they pass some different parameters, and then they end up actually getting their response. And one of the nice things that this very thin client, which is on the order of, say, 100 lines, what it actually does is, the client doesn't have to understand how to actually talk to the local Envoy. It doesn't have to understand how to do request ID propagation. And we can actually guide devs into doing good timeouts, retry, circuit breaking policies. And we have these clients for Python, Go, and PHP. Last, I did want to briefly talk about MongoDB since it's a pretty interesting case. So we use MongoDB at Lyft, and historically, we've had a lot of operational problems with Mongo, and kind of the pattern that we would often get into is Mongo uses one thread per connection. And it can get into this failure scenario where the database slows down. There's a thundering herd that basically disconnects, right? Everyone connects to Mongo, and then Mongo basically implodes. And for years, we would have, I would say, not super regular, but fairly regular 10 to 15 minute outages where we would have to kill traffic coming into Mongo. We'd actually have to potentially talk to our Mongo provider to have them shut down the database and then bring it back up. It was really, really awful. We now run Mongo in what I think is a fairly interesting way. So what we do is all of our applications that talk to Mongo, whether that be Go, PHP, or Python, they all talk through Envoy. And then Envoy actually has 3 different filters installed. We have an L4 global rate limit filter. So this allows us to rate limit the number of connections per second that are coming into Mongo. We have a Mongo sniffer. So we actually have code in Envoy that parses BSON and actually goes through and essentially spits out all kinds of different stats that Mongo itself doesn't provide. So for example, we will look at the query patterns and figure out, are they scatter gets? Are they multi-gets, right? And then we can have stats by call site that allow developers to say, ooh, we just shipped some scatter get that we don't actually know about, and then we can have people go in and actually do debugging, which is super useful. And then we actually use the normal TCP proxy filter, and that allows us to do load balancing. So what happens now is we still actually see these kind of underlying pathologies where Mongo will slow down for some particular reason. We will drop we'll drop all the connections in the client. But because of this rate limiting system, right, Envoy will block the number of connections per second that are coming back into Mongo, and the database can actually recover. And you might ask, well, couldn't we have done this in each library, right? Well, yes, I mean, we absolutely could have, but to me, this is a great example of why kind of the service mesh sidecar approach is so powerful, because we would have had to go and modify the drivers in all 3 of those applications. Some of these applications use ODMs, which makes it incredibly confusing to understand how the application code actually connects to the database. So doing it at the Envoy layer allowed us to skip touching all these applications and operate on that raw kind of stream. So this has been a great solution for us. So very briefly, just from the Envoy deployment at Lyft, we run, now this slide is old, probably over 150 services now. We run Envoy on over 10,000 hosts. At peak, the Envoy mesh does over 2 million requests per second. All service-to-service traffic goes through Envoy. We use Envoy, I've already talked about this, for MongoDB. We do something very similar for Dynamo. So we actually have a filter that parses the Dynamo REST API and spits out stats. So if you're using Dynamo, again, from any of the application languages, you get very rich stats. We use it to proxy to all of our partners. This, again, has been super useful because if we have multiple different application stacks talking to partners, it can be very, very powerful to know from a global perspective, is this partner having a particular issue? I've already showed you some screenshots. So we use Kibana as well as Elasticsearch for logging. We use a company called Lightstep for our tracing system, and we use a company called Wavefront for stats via the StatsD API. So that's it. We've had a lot of interest since we open sourced about 6 months ago. I've been honestly, truly amazed with kind of how much interest there's been. We're looking forward to getting other people kind of ramped up. We're pretty excited about it. So if you're interested, happy to chat more about it, and happy to take questions. Thank you.
So your approach of using health checks, or approach of routing traffic using health checks over service discovery is pretty interesting. But how do you guys, if the service discovery tier is failing, how do you guys know if a new server is coming in? Do you guys use internal load balancers to identify?
No, we do not use any internal load balancers at all. So the one thing that we cannot do if the service discovery system is failing is we cannot scale up.
Okay.
So the service discovery system failing is a tier 0 serious problem, but it's not a we are 100% down problem.
Cool.
Yeah.
Could you talk about how you make updates to Envoy itself in your production systems?
Yeah, so we work on Envoy fairly rapidly. We deploy Envoy a few times a week, actually. So we run master at Lyft. Envoy is capable of hot restarting, so it can do a full reload, including all code and configs without dropping any connections. So other than extreme cases, we are able to actually basically deploy Envoy, including a full code reload without any user visible impact.
Cool. So you mentioned a lot about performance, and this thing is really quite impressive. Like what are the memory requirements that we're talking about for each of these proxies? Sure.
Yeah. So when everyone asks about Perf, I'm just going to go on my little Perf rant right now. It's a very complicated question to answer because performance in terms of whether it be memory usage or CPU usage, it's very dependent on what Envoy is actually doing, right? So Envoy can do a lot of stuff. So I mean, if it's terminating SSL for an example, it's going to use a lot more memory, right, than if it's just doing plain text. Or if we have a very rich filter stack and we're doing tracing and like we're generating request IDs and doing all kinds of different things, that's going to use a lot more CPU. I will attempt to answer your question, and I kind of gave that intro because any number that I give is going to be very speculative. What I would say is that at Lyft, most of our service-to-service nodes that are potentially dealing with a mesh of thousands of connections, and those are all H2 connections, I'd say the average memory usage for the process is like 50 megabytes. So, and that's a very large mesh, right? The boot memory of Envoy on its own is probably about 2 megabytes, not very much. So it's not Java. Yeah.
Just curious about health checking. You mentioned so you're like health checking all the services.
Yep.
And as the number of services and the number of machines grows, I just wondering if you thought ahead about how you might make that more efficient.
We have, yeah. So that's a pretty interesting question, just in the sense that I think to most people they see this health checking system and a lot of people ask that question. They ask, you're doing these n-square health checks that must not scale, right? And it will definitely not scale at some n. I would argue that n is only in production at probably less than 10 companies. It'll actually scale pretty large, and it'll scale pretty large for two reasons. Health checking traffic, it typically takes place over kept alive plain text connections, so they're very low memory usage. The actual CPU usage of doing those health checks is very, very, very low. So we still do this kind of n-squared style health checking at Lyft, and we're north of 10,000 nodes. In terms of have I thought of what we're going to do when that no longer scales, yes. There's two things that we are going to do. The first thing is we're going to have built-in subsetting support within the load balancer. So basically that means that let's say that you have a source cluster and a destination cluster. You can do a bunch of math that basically will tell you from a probabilistic perspective that not every host has to talk to every other host. So we can essentially make stable decisions that say we will subset kind of the traffic out, and then we can break that n-square problem there. The other thing that we're doing is we're actually working with Google. There's a whole bunch of other stuff that I can talk about after. And one of the things that we're kind of doing with Google is we're developing kind of a general API by which Envoy can both report health as well as get instructions from a global perspective. So Google calls that their global load balancer. And what that will give us is the ability to have a centralized brain essentially do the subsetting. So moving forward, we will end up doing subsetting. It'll either be done by Envoy internally or it'll be done by a global load balancing central brain component.
Hi. Excuse me. So I really liked the health status you showed between two services, for example, that a developer could pick. Why use an approach like that in place of something like a global call graph where this developer could just go drill down to see where a particular problem is? Is there like an advantage to using this versus this?
Sorry, a global call graph like...
It shows just the global stats of all the communication among all the services you have.
I see. So I would love that. That is something that we are going to build. So we actually have this thing internally, which I didn't show. It's called InfraViz, and it takes all the information from Envoy and it builds kind of like a basic core diagram and like kind of a call graph. Someone built it during a hack project. It's not very nice. So I would love that. I think that would be amazing. All of the data is there, but someone who knows how to build UIs has to come and actually build it. So it's not that I don't want it, it's just that no one has built it yet. Yeah.
Just as a quick note, I first heard about this on the Software Engineering Daily podcast, so the people listen to that interview. Just want to throw that out there for you. But have you toyed around at all with the idea of using Envoy in a processing cluster scenario, whether that be like within the nodes for Hadoop, or even just something as simple as a Jenkins master and slave situation?
We have not. I don't like Envoy is pretty flexible, so I don't see any reason that it couldn't be. It's just not something that we have done yet.
Okay,
yeah.
Just curious.
Yeah.
So I'm kind of curious for containerized workloads where you might have a single node running multiple applications. Do you guys have an opinion on how you should deploy Envoy, whether or not it should be in the container or outside the container? There's been a giant discussion on this with people on, this is a religious battle of people who want it to be pod level from the Kubernetes speak to node level. I think
I've been kind of out of this conversation because we don't actually use containers in prod at Lyft, so I don't have a vested interest yet. I think people are converging on pod or per application level deployment mainly because it's easier to reason about, if you're dealing with billing, if you're dealing with security, if you're dealing with deployments, there's a whole bunch of reasons that it's better from a pod perspective. So there's a project called Istio, and that's a Google project that's coming out, and that's going to use Envoy as the underlying proxy, and that'll bring Envoy to Kubernetes. And for that, they're doing pod level deployment.
Hey, I really enjoyed your talk. So my question centers around why did Lyft choose to write Envoy internally? The two examples I'm thinking of is there's a competing, seemingly similar project called Linkerd, and aside from that, why didn't you choose possibly other open source projects like OpenResty, for instance, and then implementing that in Lua and, say, in Nginx? And I'm curious to hear the thought process around that decision.
Sure. So when it comes to Linkerd, we were working on Envoy before Linkerd was actually open sourced. So that's one. To be totally frank, I think writing a component like this in a language like Java is absolutely insane. So I just like that alone is a total non-starter. From like an Nginx perspective, and to do something like Kong or something like that, or like OpenResty, written in Lua, I think our experience. So it's a little complicated because this is, at least from an intellectual perspective, this is based on work that was done back at Twitter that wasn't open sourced. So we were reasonably sure that we could do something at pretty high quality relatively quickly based on work that had been previously done. And I think from a robustness perspective, having it all be written in native code and not rely on a kind of a scripting engine has benefits, and Perf also. What's been really interesting for us since we open sourced is I thought when we open sourced that there was going to be a lot more people coming out and saying, why did you not use Nginx? And I have been very surprised at how few of those people there are. In fact, I would say it's the opposite. I have had so many companies come and say, thank you that there's something other than Nginx, right, that we can basically work with. Because Nginx is super fast. Like if it works for you out of the box, it's great, right? I highly recommend it. Nginx from a development perspective is not so great. Like to actually work on it, like from the native code perspective, how they do development, like how they do testing, all of that, it's not great. So there's been a huge desire for people to come and work on a code base that's a little more modern, a little more well-designed, and I think we're seeing a lot of interest based on that. Yeah.
Thanks.
Sure. Cool. Well, thank you very much. Yeah.